And in this area, we have alpha and beta, two phases. We have some narrow regions at the left and right side of the diagram. One is alpha solid solution, pure alpha. We have only single phase here, which is alpha. We have another and similar region at this side of the diagram, which is pure beta. We have liquid phase, and maybe the most important thing in this diagram is this point, which is the eutectic point. And as you can see, there is a specific composition for this point and a temperature related to this. And this is the minimum melting point of this system. It says the concentration is less than 2%, means that we are in the alpha region. We are in alpha region to the room temperature. Okay, so when the T is 330, which means that we are in the
greater than 330.
Yes, more than TL. The temperature is more than TL, means that we have only one phase, which is liquid at this point. Then we are cooling the system. We are moving toward solidification, and we reach to this point, which is in the
phase
L plus alpha region, and we have two different phases. So in this region, as you can see here in this schematic, we have two different phases, one L, the other one is alpha.
So you are showing part of that, yeah?
Yes, we are showing part of this, and we are in L plus alpha region. So the tie line starts from alpha, the composition point, and then liquid. So this is the time.
But right beneath this E point, E is here, yeah?
Yes, E is here. Okay, so what is your question?
Again, we have another phase, which is alpha plus beta, yeah?
No.
It's this line.
Okay, but we are at this temperature, right? This is a lower temperature that you are talking about. We will talk about that later, but for now, we are in this range, somewhere from here to here, more than this temperature, which is 183. Any temperature between these two, when we draw a tie line, we have two phases, L and alpha.
Okay, imagine you're talking about this part, yeah? Am I right? Yeah, it's between 0 and 30%, yeah?
Yes, and temperature-wise, we are more than this TE. The temperature is higher than...
Oh, I see. I got that.
Okay? So we are in L plus alpha region, two different phases. Okay? So two different phases, and let's get back to the...
Eutectic line, that which passes through the eutectic point from each side. Intersect with the alpha and beta at maximum solubility point, or no? It's not necessary.
I didn't get your question.
I mean, in this picture, okay, we have a eutectic line.
Eutectic line, you are saying?
Yes, eutectic line.
Eutectic temperature, this one, right?
Yes.
Okay.
It is eutectic line or not? Then its name is eutectic line or no? Because we have eutectic point. Okay, what we
point, and this is the temperature line we have at the eutectic point. Okay.
Okay. Is it necessary or is it correct that we say this line from left side intersect with alpha at the point which is maximum solubility of beta in alpha, and from the other side
maximum solubility of SN in
PB. In PB,
yeah,
sorry, yes,
which is alpha, and here beta. Yes, it is exactly.
It's correct.
Yes, and this is completely that we can see clearly from the phase diagram. As I said, it works like a map.
Yes, it's a quick question for the A, aluminum and magnesium. We know that magnesium going to get corrosion first, but can we say that magnesium gets corrosion first and aluminum after magnesium's completely corroded?
Yes. Yeah, completely true. In all of these cases, when we have two coupled metals, For example, the A, aluminum and magnesium, and B, zinc and iron. When the zinc is completely corroded, means all of the zinc pure metal has been converted to zinc oxide, or in this case, magnesium has been changed or converted to magnesium oxide. So now it is the aluminum turn to be corroded, right? So first, the more active metal will be corroded. If all of them has been changed to the oxide, then the other one is under corrosion.
So considering this answer, can we say for the first question, do you remember it was the metal siding, aluminum sidings fastened with the steel or metal screws? Can we say that all the sidings corroded first, then corrosion wise?
Okay.
They can say that. I'm not sure.
I don't want to say no, because from the question, it could be one of the reasons. So, but in this case, the question is very tricky, because question it's question saying that we have two parts. One part, for example, let's get back to this one. We have zinc and iron. Corrosion is, when we talk about corrosion is usually happening in metals and metallic materials, and the destruction and deterioration of the metals or of metals or alloys by the environment, such as humidity, air, water, and this stuff, through chemical or electrochemical changes. So we have from left to right, we have a metal ore which is converting to metal, and we call this metallurgical extraction, when we are extracting a metal, for example, aluminum from aluminum oxide or iron from iron oxide. But from the right to the left is corrosion, when a metal is converting to a metal oxide.
Magnesium lose electrons. We should write Mg.
Exactly.
Mg, I don't know. It has 2 electrons. Mg2.
No, you know, because it says use an electrochemical balance of 2, right?
2, yes.
So it should be
Mg2 plus plus 2 electrons, and then yes.
The anode reaction for magnesium, which is sacrificial anode and undergoes oxidation, and the half cell reaction at the anode, it is the reaction that we have at the anode. Mg, pure magnesium, is undergoing oxidation or corrosion, and from the question we know that the valence is 2, so Mg is converting to Mg2 plus 2 electron. Mg2 positive plus 2 electron, and the magnesium atom loses 2 electrons to become a magnesium ion, as specified by the electrochemical valence of 2. So this is the answer for A, which is very simple and easy and straightforward, okay? But how about B? What is the average corrosion current supplied by the anode? Talking about a corrosion current.
I think we should calculate this 0.8 kilograms magnesium. How much electrons actually maybe it lose, and then using 15 years